Picture this: a tiny, gumdrop-shaped spacecraft, barely larger than a small car, screaming in from the moon at an unimaginable 25,000 miles per hour. That's 10 times faster than a rifle bullet, folks, and it's about to slam into Earth's thin, blue atmospheric shell so hard its heat shield glows at a searing 5,000 degrees Fahrenheit. That's half the surface temperature of our very own sun. You get one shot, one heat shield, 0-second chances to get this right. And here's the kicker. Instead of just belly flopping straight down, this craft is something utterly unprecedented. It skips off the atmosphere like a perfectly thrown stone across the pond, bleeding off energy in a maneuver no human-rated ship has ever dared to attempt. This isn't science fiction, my friends. This is exactly what NASA just pulled off with the uncrewed Artemis 1 Orion capsule. And today, we're going to unpack every single nut, bolt, and white-hot photon of that incredible, record-breaking ride. Are you ready to see how we go from the moon to a gentle splashdown without becoming a spectacular, albeit tragic, shooting star? Let's dive right in. This isn't just a story about a spacecraft. It's a story about pushing the boundaries of what we thought was possible, a testament to human ingenuity and a crucial step on our journey back to the moon and beyond. The problem we had to solve. Now, for those of you who remember the Apollo missions, their re-entries were brutal, no doubt, but relatively straightforward from a trajectory perspective. They'd come in steep, take the hit, and parachute down. A direct ballistic entry. Simple, effective for its time, but with some serious limitations. Artemis, though, is a whole different beast. We're not just coming back from low Earth orbit this time. We're hauling back from the moon. What does that mean in practical terms? Well, it means double the speed compared to a low Earth orbit return, which, thanks to the physics of kinetic energy, mass times velocity squared, remember, translates to 4 times the kinetic energy. And that, in turn, means way more heat to shed. A direct Apollo-style entry from lunar velocity would be catastrophic for a crew. First, you'd spike the G-forces past what even the toughest astronaut could reasonably handle, potentially causing loss of consciousness or serious injury. Imagine being slammed against your seat with the force of 6 or 7 times your body weight for an extended period. Not exactly a pleasant homecoming. Second, that immense heat would concentrate onto one relatively small patch of the heat shield, pushing it beyond its design limits and risking structural failure. And third, you'd land thousands of miles off target, turning a precision recovery operation into a frantic, open ocean search and rescue mission. So the problem was clear. If we wanted crews to return alive, land accurately, and eventually enable reusable spacecraft, we needed a much slicker, more sophisticated dance move for reentry. We needed to fundamentally rethink how we brought a human-rated vehicle back from deep space. And that's where the ingenious concept of the skip entry enters the stage, ready to solve some of the most daunting challenges in spaceflight. It's not just about getting home. It's about getting home safely, reliably, and precisely every single time. What a skip entry actually is. All right, let's break down this skip entry concept because it's genuinely brilliant. Think back to your childhood, or maybe just a leisurely afternoon by a lake. You pick up a flat, smooth stone, flick it just right across the water surface, and what happens? It kisses the surface, hops up, loses a bit of speed, maybe hops again, and then eventually settles down. Orion does the exact same thing, but instead of a tranquil pond, the water is Earth's incredibly dense, albeit thin, upper atmosphere. Here's the engineering magic. As Orion slams into the atmosphere, it doesn't just plunge straight down. Instead, its flight control system, with incredible precision, tilts the capsule to generate a small amount of aerodynamic lift. This lift is just enough to make the capsule skip back out of the densest part of the atmosphere, momentarily returning to a very shallow arc in space. During this brief skip phase, it continues to shed a tremendous amount of velocity in the vacuum of space without the crushing g-forces or extreme heating of a continuous atmospheric plunge. Then, after this short arc, it re-enters for the final, gentler descent. It's like taking 2 bites at the breaking apple rather than trying to swallow it whole. This strategy offers multiple critical advantages. Lower peak heating on the heat shield because the energy is dissipated over a longer time and larger area. Significantly gentler g-forces on the crew, making the ride much more tolerable. And perhaps most impressively, incredibly precise steering. The math behind this maneuver is viciously complex. The angle of attack has to be maintained within a fraction of a degree, a truly mind-boggling feat of guidance and navigation. But the payoff is enormous. Instead of scattering across an entire ocean, Orion can land within a few miles of its recovery ship, turning a logistical nightmare into a manageable, pinpoint operation. It's a testament to the power of precise engineering and a profound understanding of aerodynamics, even at hypersonic speeds.
The numbers that make your jaw drop. Let's talk numbers, because these aren't just figures. They're a testament to the extreme forces at play and the incredible engineering that tamed them. When Orion first hit Earth's atmosphere, it was traveling at an eye-watering 11 kilometers per second. That's roughly 25,000 miles per hour, or Mach 32. To put that in perspective, a commercial airliner cruises at about Mach 0.8. We're talking about speeds that defy everyday comprehension. During the peak deceleration phase, the crew would have experienced about 4 Gs. Now, 4 Gs might sound like a lot, but it's well within the limits of what a moon-worn crew can comfortably handle, especially compared to the 6.5 Gs of Apollo. It's a firm push into your seat, but not a bone-crushing, blackout-inducing force. The outside temperature on the heat shield surface, a scorching 2,800 degrees Celsius. That's about 5,000 degrees Fahrenheit. To give you a sense of that heat, molten lava is around 700 to 1,200 degrees Celsius. We're talking about temperatures hot enough to melt titanium, vaporize steel, and make solid rock turned into gas. This isn't just hot, it's an inferno designed to be endured. The total amount of energy that heat shield had to swallow and dissipate was roughly 60 gigajoules. What does 60 gigajoules feel like? Imagine a fully loaded freight train rumbling down the tracks, suddenly slamming into the side of a mountain at full tilt. That's the kind of energy we're talking about, converted from kinetic energy into heat and noise in mere minutes. All of that immense energy, equivalent to the power output of a small city for several minutes, gets shed in under 8 minutes during the entire re-entry sequence. Try getting your car's brakes to do that kind of work without melting into slag. These aren't just big numbers. They represent a triumph of material science, thermal engineering, and precise flight control, allowing us to bring humans safely home from the void. Heat shield drama and fixes. Even with all that incredible engineering, spaceflight is a relentless teacher, and Artemis 1, while proving the skip entry concept works beautifully, also exposed a little gremlin in the details. The Avcoat sacrificial layer, which is designed to char and abrogate away, did its job, but it charred, cracked, and popped off in bigger flakes than NASA's sophisticated computer models had predicted. Engineers call this elevated spallation. Basically, gases generated by the intense heat bubbled up inside the Avcoat material, pressurized, and then blew off crumbs of the shield in larger pieces. Now, don't get me wrong, the capsule still made it home intact. The heat shield did its primary job of protecting the vehicle and its future occupants. But for crewed missions, intact isn't enough. Perfectly functioning is the goal. So for Artemis 2, which will carry astronauts, NASA isn't taking any chances. They're tweaking the trajectory to reduce the dwell time in the skip phase. This means less time spent in the densest part of the atmosphere during the initial dip, which in turn should minimize the gas buildup and pressure that caused the spallation. It's a subtle but critical adjustment to the flight profile, a testament to the iterative nature of space exploration. Looking further ahead to Artemis 3, the mission that will put humans back on the lunar surface, they're going even deeper. They're baking the heat shield with a new resin that's designed to be more permeable. This new chemistry will allow those internal gases to vent more easily before pressure can build up and cause spallation. It's not a complete redesign of the heat shield, which would be a monumental undertaking and introduce significant delays. Instead, it's a smart, targeted evolution. Smarter chemistry combined with smarter flying. These incremental improvements, born from real-world data and meticulous analysis, are how we push the boundaries of safety and reliability in deep space exploration. It's all about learning from every flight, no matter how successful, to make the next one even better. How the skip compares to Apollo. Let's put the Artemis skip entry into historical context by comparing it to its predecessor, the Apollo re-entries. Apollo capsules, coming back from the moon, used a single, steep, -6.5-degree dive into the atmosphere. This was a brute force approach, effective but demanding. Astronauts endured peak deceleration forces topping out near 6.5 Gs, a truly punishing experience that tested the limits of human endurance. And while Apollo was a monumental achievement, its re-entry precision wasn't quite as refined. Capsules could land up to 300 nautical miles off their target recovery zone. This necessitated massive naval task forces spread across huge swaths of ocean, waiting to pluck the astronauts from the sea. It was a logistical marvel in itself, but incredibly resource-intensive. Orion's skip entry, by contrast, is a symphony of precision and control. It pulls significantly less Gs, topping out around 4 Gs, a full 1.5 Gs less than Apollo. This translates to a much gentler ride for the crew, reducing fatigue and the risk of injury after a long mission. But here's where the real game changer comes in. Orion can land within a mere 5 nautical miles of its target. Think about that. From a journey of nearly 250,000 miles, it can hit a spot with astonishing accuracy. This precision drastically simplifies recovery operations, requiring a much smaller, more focused team. Furthermore, this skip entry spreads the heat load over a wider footprint and a longer duration, while Apollo concentrated the inferno onto a smaller area for a shorter, more intense period. Orion's method allows the heat shield to work more efficiently, enduring less peak stress. Apollo needed a sprawling Navy task force, a veritable fleet to cover its wide potential landing zones. Orion, on the other hand, can nail a spot the size of a shopping mall. This matters immensely when you're planning to splash down within helicopter range of San Diego for one flight and perhaps the coast of Ireland for the next. This isn't just an engineering upgrade, it's a fundamental shift in how we approach deep space returns, making them safer, more efficient, and far more adaptable for future missions. Guiding a falling house. Guiding a spacecraft at hypersonic speeds through the upper atmosphere is often likened to trying to fly a brick with a barn door. It's not exactly designed for elegant aerobatics, yet Orion manages to do it with incredible grace and precision, thanks to a sophisticated guidance system. It doesn't have wings, so it can't bank and turn like an airplane. Instead, Orion uses a combination of 12 powerful thrusters and a weighted lift vector. How does that work? The capsule isn't perfectly symmetrical. It's designed with its center of gravity slightly offset. This creates a small amount of aerodynamic lift as it flies through the atmosphere.
By rolling the capsule around its axis, Orion can change the direction of that lift. Imagine a tiny, invisible wing. If you roll the capsule, you can point that wing left, right, up, or down. This allows the craft to tweak its cross range, effectively steering itself towards the target landing zone, much like banking a plane, but without any actual wings. It's a subtle dance of aerodynamics and propulsion, executed with split-second timing. Now, during the most intense part of reentry, when the capsule is glowing like a meteor, the air around it becomes superheated plasma. This plasma creates a communications blackout, meaning GPS signals can't penetrate it. So, how does the nav computer know where it is and where it's going? It relies on an ingenious fusion of internal navigation sensors, star trackers which precisely measure the capsule's orientation by locking onto celestial bodies, are key before reentry. Once in the atmosphere, gyroscopes provide critical attitude information, and atmospheric pressure sensors help determine altitude and speed. The computer constantly fuses all this data, even during blackout, to keep Orion on its precise trajectory. Once the speed finally drops below Mach 3, the plasma sheath dissipates and communications are restored. That's when the next critical phase begins, the parachute deployment. First, 2 small drogue parachutes pop out, stabilizing the capsule and slowing it from hundreds of miles per hour. Then, the 3 massive main parachutes unfurl, blooming into giant colorful canopies. This sequence takes the craft from around 300 miles per hour down to a gentle 20 miles per hour splashdown speed in 2 staged jerks. These decelerations are carefully choreographed to be gentle enough to protect the astronauts' necks, ensuring that after an epic journey, their landing is as soft as possible. It's a marvel of automated precision, turning a hypersonic brick into a feather-light descent. What this means for Mars. The Artemis program isn't just about returning to the moon. It's explicitly designed as a stepping stone to Mars. And the skip entry technique, perfected here on Earth, is absolutely critical for our eventual journey to the red planet. Why? Because Mars presents its own unique and formidable atmospheric entry challenges. While Earth's entry velocities from the moon are around 11 kilometers per second, Mars' entry velocities start at a slightly lower but still incredibly high 7 kilometers per second. The real trick, though, is Mars's atmosphere. It's incredibly thin, about 1% the density of Earth's atmosphere. This means that while it's thick enough to cause significant heating and drag, it's not dense enough to slow a spacecraft down quickly through aerodynamic braking alone. It's like trying to brake a car by dragging a feather. This is precisely where the skip entry, or a similar modulated atmospheric entry, becomes indispensable. Practicing and validating the skip entry at Earth, with its denser atmosphere, allows engineers to fine-tune and prove several critical technologies and algorithms. First, it lets them validate the guidance algorithms that precisely control the capsule's angle of attack and lift vector. These algorithms will need to be adapted for Mars's thinner air, but the foundational principles and control loops are the same. Second, it validates the thermal protection systems, the heat shields. While Mars entry will be different, understanding how materials behave under extreme heat and pressure and how to manage that heat is directly transferable. And third, it validates the lift modulation techniques, allowing future Mars vehicles to dissipate energy over a longer period and achieve pinpoint landings. Without a technique like the skip entry, a direct entry into Mars' thin atmosphere would either result in a brutal high-G deceleration, if you try to slow down too fast, or an uncontrolled thousands of miles off-target landing. Every Artemis skip entry is, in essence, a dress rehearsal. It's not just for getting home from the moon. It's about nailing a pinpoint Mars landing without cratering the crew or their precious cargo. It's a vital piece of the puzzle, ensuring that when we finally send humans to Mars, they'll have the best possible chance of a safe and precise arrival. Artemis 2 and 3 Preview. The success of Artemis 1 wasn't just a triumphant conclusion,
It was a powerful launchpad for what comes next. Artemis 2, currently scheduled for next year, will be the first crewed mission of the program. 4 brave astronauts will embark on a journey around the moon, tracing a similar trajectory to Artemis 1, and crucially, they'll be brought home using the exact same skip entry profile. This mission isn't just about proving the hardware, it's about proving the entire system, including the human element, can safely execute this complex maneuver. The data gathered from Artemis 1, particularly regarding the heat shield, is directly informing flight preparations for Artemis 2, ensuring the crew safety is paramount. Then, looking a little further out, Artemis 3 is targeted before 2030, and this is the mission that will make history by returning humans to the lunar surface, specifically to the moon's south pole, a region believed to harbor significant water ice. After their historic lunar landing and exploration, the Artemis 3 crew will face an even more demanding re-entry challenge. They'll have spent a longer time in lunar orbit, potentially performing more complex operations, which could mean a slightly different, perhaps even steeper re-entry profile as they return home. Each mission builds on the last, pushing the boundaries of experience and technology. What's truly exciting is how quickly lessons from Artemis 1 are being integrated. For instance, the data from Artemis 1 already allowed engineers to shave a significant 200 kilograms of heat shield mass from the lander adapter. Think about that, 200 kilograms of weight saved. In spaceflight, every gram counts, and 200 kilograms is a massive saving. This isn't just a minor tweak, it's a tangible, impactful gain. That mass budget can now be traded for more critical resources, more food and supplies for the crew, more scientific samples to bring back from the moon, or even additional safety margins and contingency equipment. It's a direct example of how uncrewed test flights like Artemis 1 are invaluable, providing real-world data that refines future missions and makes them safer, more efficient, and more scientifically productive. The drumbeat of progress is getting louder, and each mission is a vital step on this incredible journey. Broader ripple effects. The impact of Artemis 1 and its groundbreaking skip entry technology isn't confined to NASA's walls or the Artemis program alone. This isn't just an internal success story, it's generating broader ripple effects across the entire space industry and beyond. The technology, the algorithms, and the lessons learned are not staying in-house. We're already seeing commercial lunar landers and even some private spaceplane ventures licensing and adapting the skip entry algorithms. Why reinvent the wheel when NASA has just proven a highly effective, human-rated solution? This transfer of technology accelerates commercial space development, making lunar missions more feasible and safer for private entities. It's a classic example of government-funded research yielding benefits for the entire ecosystem. Beyond commercial applications, universities are actively adapting the plasma telemetry data and atmospheric entry models for their own hypersonic flight experiments. Understanding how to communicate through a plasma sheath or how materials behave under such extreme conditions is crucial for developing future high-speed aircraft and re-entry vehicles. The data from Orion's fiery return is providing invaluable real-world validation for theoretical models and laboratory experiments, pushing the frontier of aerospace research. And let's not forget about the improvements in thermal protection. Every breakthrough in heat shield technology, every refinement in how we manage extreme heat during re-entry translates directly to greener, more reusable rockets here on Earth. If we can protect a capsule returning from the moon, we can certainly improve the durability and reusability of first-stage rocket boosters that re-enter Earth's atmosphere at much lower speeds. This means less waste, lower operational cost, and ultimately more sustainable access to space for everyone. One mission, one record-breaking reentry, and suddenly many industries are lifted, benefiting from the innovation forged in the crucible of deep space. It's a powerful reminder that space exploration isn't just about what's out there. It's also about how it improves life right here on Earth. CTA 1. If you're enjoying this deep dive into the incredible engineering and daring spirit behind Artemis, and you want more straight-to-the-point space engineering explainers, do me a favor, smash that like button and subscribe to the channel. That way you won't miss the next chapter when Artemis 2 finally carries its crew around the moon. Your support helps us keep bringing you these stories of human ingenuity. Myths we can bury. With any groundbreaking achievement, especially in space, myths and misconceptions tend to crop up. So let's take a moment to debunk a few common ones about the skip entry and Artemis 1. Myth 1. Skip entry is brand new. Nope, not entirely. While Orion is indeed the first built-for-humans craft to risk and successfully execute this complex maneuver, robotic probes actually did it decades ago. Back in the 1970s, Soviet Venera probes used a form of skip entry when descending into Venus's incredibly dense atmosphere. Even some early atmospheric reentry vehicles experimented with similar concepts. However, adapting this for a large, human-rated capsule with all the safety redundancies and precision required is a monumental leap. So while the concept isn't altogether novel, its application to human spaceflight from deep space is absolutely revolutionary. Myth 2. We could just use bigger parachutes. This one sounds logical, right? If you need to slow down, just use a bigger parachute. But here's the fundamental flaw in that thinking. Parachutes only become effective after you've already killed about 99% of your speed. They operate in the lower, denser parts of the atmosphere, where aerodynamic drag can actually inflate them without tearing them to shreds. They do absolutely zilch for the initial hypersonic plasma fireball phase of reentry. You can't deploy a parachute at 25,000 miles per hour. It would vaporize instantly. The heat shield and the skip entry are what manage that initial incredibly violent deceleration. Parachutes are the soft landing, not the primary brake. And myth 3. Heat shields last forever. Oh, if only that were true. The reality is far more dramatic. Every single reentry is effectively a one-way erosion party for the heat shield. The Avcot material is designed to char and ablate away, taking the heat with it as it sacrifices itself to protect the capsule. It's a beautifully engineered but consumable component. Refurbishing a heat shield after it's been subjected to 5,000 degrees temperatures and extreme ablation is, for now, strictly in the realm of science fiction. Each mission requires a brand new, meticulously crafted heat shield. The dream of fully reusable reentry systems is still a distant goal, requiring entirely new materials and design philosophies. So, no. They definitely don't last forever, and that's precisely by design.
How close we came to losing Artemis 1. Even with all the meticulous planning and flawless execution, spaceflight always holds a few nail-biting surprises. Artemis 1 was no exception. Halfway through that critical skip entry maneuver, a moment when precision was paramount, a thruster valve on the Orion capsule decided to stick open. This wasn't just a minor glitch. It meant that precious propellant was bleeding away, uncontrolled, at a critical juncture. The flight software, however, proved its mettle. It immediately detected the anomaly and, with incredible speed and autonomy, pivoted to an emergency roll-only profile. Instead of using multiple thrusters to adjust its orientation and steer, it relied solely on rolling the capsule to achieve its steering objectives, conserving fuel for the absolute necessities.
This quick-thinking software adjustment was crucial for preserving enough propellant for the final, precise steering burns needed to hit the recovery zone. Controllers on the ground watched with bated breath. Another 30 seconds of that valve being stuck open, another half-minute of uncontrolled fuel loss, and Orion might have overshot its designated Pacific recovery zone. That would have forced a frantic, complex scramble to remote waters, potentially delaying recovery and adding significant risks. It was a gamble, a moment of high tension. Fortunately, as if responding to the collective will of the mission control team, the valve unstuck itself, just in time. The crisis averted, and the rest, as they say, is history. This incident serves as a stark reminder that even in the most technologically advanced endeavors, the margins are often measured in heartbeats. It underscores the incredible robustness of the Orion design and the brilliance of the flight software, which truly saved the day. The human element. While Artemis 1 was an uncrewed mission, it was anything but devoid of the human element, or at least the data needed to protect future humans. Instead of astronauts, the Orion capsule carried a very important passenger, a mannequin, affectionately named Commander Munikin Campos. But this wasn't just any dummy. It was kitted out with an array of sophisticated sensors. Radiation sensors were strategically placed to measure the exact doses future crews would experience during their journey beyond Earth's protective magnetic field. Vibration accelerometers were strapped to its seat, meticulously recording every jolt, shudder, and G-force experienced during launch, the skip entry, and splashdown. The data returned from Commander Munikin Campos was incredibly reassuring. It showed that a human crew would have felt vibrations akin to a moderate roller coaster ride. Exciting, perhaps a little intense, but well within tolerable limits for trained astronauts. More importantly, the radiation sensors indicated that the crew would have absorbed less radiation than a typical dental X-ray. Think about that. A trip to the moon and back through the Van Allen belts and deep space, exposing you to less radiation than a routine visit to the dentist. This data is absolutely vital. It's definitive proof that the skip entry doesn't just spare the ship from the brutal forces of reentry, it spares the people inside. It validates the design choices, the trajectory planning, and the thermal protection systems as being truly human-rated. It means that when Artemis 2 launches with its crew, they can do so with a higher degree of confidence, knowing that the ride, though intense, is survivable and designed with their safety and well-being as the utmost priority. The human element, even in an uncrewed test flight, was central to the mission's success and its future implications. Cost breakdown. Let's talk about money. Because space exploration, especially deep space exploration, is undeniably expensive. But it's also an investment in our future, and understanding the cost breakdown helps put things into perspective. Each individual heat shield tile on Orion, those critical pieces of ablative material that take the brunt of the re-entry inferno, runs about $8,000. And Orion uses approximately 380 of them, meticulously attached and inspected. Do the math, and the total cost for the heat shield alone comes out to roughly $3 million per mission. Now, $3 million sounds like a hefty price tag for what is essentially a sacrificial component. But let's compare it to the alternative. The Orion capsule itself, a marvel of engineering capable of taking humans to the moon and beyond, is estimated to cost around $4 billion. Losing that capsule due to a heat shield failure would be a catastrophic financial and programmatic setback. In that context, $3 million for the heat shield isn't just justified, it's seen by NASA as incredibly cheap insurance. It's a relatively small investment to protect an immensely valuable asset, and more importantly, the lives of future astronauts. This perspective highlights the economics of spaceflight. You invest heavily in critical components to ensure mission success and crew safety. And while the long-term goal is always to reduce costs by reusability, for now, the alternative of building an entire new moonship after a failure makes the heat shield cost a clear bargain. It's a pragmatic approach to managing risk and resources in an endeavor where the stakes are literally out of this world. The cost isn't just a number. It's a reflection of the value we place on pushing the boundaries of human exploration and ensuring the safety of those who dare to venture into the cosmos. What comes after Artemis? The Artemis program is not just about a few individual missions. It's a long-term, ambitious strategy for sustained human presence in deep space. And after the initial lunar landings, the next big piece of the puzzle is the Gateway. Imagine Gateway as a mini space station orbiting the moon. It won't be a permanent habitat like the International Space Station, but rather a crucial waypoint and outpost. Astronauts traveling from Earth aboard Orion will dock with Gateway, transfer cargo and supplies, and then, crucially, transfer to a lunar lander for the final descent to the moon's surface. This modular approach has significant implications for future skip entries. Once Gateway is operational, many future skips won't originate directly from the lunar surface. Instead, they will originate from Gateway itself, which will be in a much higher, more distant orbit around the moon, potentially even at a Lagrange point, a gravitationally stable location in space. This means that the return journey to Earth could involve even higher re-entry speeds than Artemis 1 experienced. Coming from these distant orbital points, the incoming velocity could be significantly greater, pushing the boundaries of thermal protection and re-entry dynamics even further. To meet these evolving challenges, engineers are already looking ahead, pushing the envelope of material science. They're actively testing advanced carbon-carbon composites, materials capable of withstanding temperatures rated for an astonishing 3,500 degrees Celsius, over 6,300 degrees Fahrenheit. This is significantly hotter than what the current AFCODE shield is designed for. The ultimate goal here is not just to survive re-entry, but to achieve a truly reusable heat shield. Imagine a heat shield that can fly dozens of moon laps, enduring countless infernal re-entries before needing retirement. This would revolutionize deep space travel, drastically reducing costs and turnaround times, making sustained lunar and eventually Martian operations a far more viable reality. The future of Artemis is about building the infrastructure for permanent exploration, and that means continuously innovating every single component, right down to the fiery shield that bring our explorers home.
Your role in this story, you might be thinking, this is all great, but what does it have to do with me? Well, here's the thing. Space exploration, especially something as ambitious and long-term as Artemis, thrives on public interest and support. Your role in this incredible story is more significant than you might imagine. Every view on a video like this, every share on social media, every classroom question from a curious student, these actions accumulate. They demonstrate to policymakers and decision makers that there's a genuine widespread interest in space. This public engagement, this collective curiosity, directly influences funding decisions. It nudges Congress to keep the Artemis line item alive, to ensure the budgets are there to continue these vital missions. Without sustained public interest, even the most groundbreaking scientific endeavors can falter. Space exploration isn't just a spectator sport. It's not something that happens out there while we just watch. It's a relay race, a continuous journey of discovery where the baton is curiosity itself. We, as a society, pass that baton from generation to generation. When you engage with these stories, when you share your enthusiasm, you're not just consuming content, you're actively participating in the narrative. You're helping to inspire the next generation of engineers, scientists, and astronauts who will carry that baton even further.
Your interest fuels the future, ensuring that humanity's quest to explore, to understand, and to push the boundaries of what's possible continues onward. So, passes on. Let's keep that spirit of exploration alive and thriving. Conclusion. Wrap up. So, the next time you find yourself skipping a flat stone across a calm lake, take a moment. Remember that humanity, with audacious vision and incredible engineering prowess, just skipped a 5-ton spaceship across the very edge of Earth's atmosphere. We brought it home from lunar velocity, slowing it from an unimaginable speed to a gentle, precise ocean kiss. Artemis 1 wasn't just a mission, it was a declaration. It proved that what once seemed impossible is now just another engineering checklist item meticulously planned and brilliantly executed. Artemis 2 is already on the horizon, ready to add the invaluable human element to this incredible journey. 4 astronauts will follow in Orion's wake, proving that we can not only send our machines, but also our people safely to the moon and back. And then Artemis 3 will achieve the ultimate goal, adding human footprints to the lunar South Pole, opening up new frontiers of scientific discovery. Each successful skip entry, each meticulous maneuver, each lesson learned from these pioneering missions carries us one hop closer to making boot prints on Mars a reality. This isn't just about reaching a destination, it's about mastering the journey. If that doesn't light your rocket, if that doesn't stir a sense of awe and excitement within you, well, frankly, you might want to check your pulse. The future of exploration is here and it's electrifying. Thanks for riding along with me on this deep dive. Don't forget to subscribe for more. Drop your questions and thoughts in the comments below, and I'll see you at the next launch.